So just like mass stoichiometry, and for all solution gas and mass stoichiometry, we always do these 3 steps. So we're always grabbing, we've done mass, and now we're going to be doing concentrations, and we'll be doing gas as well. So we're doing a mass to, a concentration to a moles. We've done mass to moles. And then at the end, we've already done moles to mass, and now we're going to do moles to concentration. They could ask for moles to volume or something else, but you've got options here. And then, of course, in the middle, we always do a ratio conversion. If it's 1:1, you can just make the statement that it's the same. And so if we're sticking strictly to just solution, starting with a concentration and finishing with a concentration, we are always going to use this formula here. So converting the concentration to number of moles, and then at the end, converting the number of moles to a concentration. And then, of course, the mole ratio in the middle. So here we have a practice problem. We have a volume of this one, and we have a volume and concentration of this one. So this is technically a titration, though you don't need to know that yet. So finding out the concentration of an unknown substance using the concentration of a known substance. And so let's get the number of moles out for this one. So labeled formula, number of moles of sodium hydroxide, C on V. Put the substitutions in there. So we've got 0.025 litres and the concentration, and that gives us the number of moles. Middle step, 1 is to 2 moles, and so x to 250, cross multiply that. And so 1 times this equals 2x, divide both sides by 2, and that's how many moles of sulfuric acid we have. And now we can do the concentration because we know we've got 0.02 litres. And so labelled formula, substitution, correct sig figs with units. And there we go. It's 0.0625 moles decimeters -3 of H2SO4. Okay, now this one's not strictly in your syllabus, but you need it to do your dilutions and your IAs potentially. So if you have like a 3 molar solution or 2 molar stock solution, you need to make increments so that you can test various concentrations, or you may want a various concentration as a control. So how do you make like these sort of concentrations? So we use this formula here. So the number of moles before equals the number of moles after. All that you're doing is changing the volume. And if you change the volume, what you're going to end up with is just a different concentration. You have the same number of moles before and after, but you're going to add a different amount of water to it, and therefore you're going to get a different concentration. So that's the trick of the formula. Please don't use this for stoichiometry. I've seen that used quite a bit. If everything's 1:1 ratio, you can actually use this for stoich, but don't ever do that. Just use it for dilutions. And so the key is, what you're going to do is usually you're going to have, the concentration and volume that you want. And then so you're trying, and the concentration you start with. So you're just working out the volume that you need of a known concentration to make up to a certain volume to give that certain concentration. So that's quite important that you understand what this all means. So there's a practice question here. So say you were given 12 molar HCl, which you won't because it's too strong. And then what you actually want for your experiments is you need a whole litre of 0.05 molar solution. So write down the variables if you need to, but this is the formula, C1V1 equals C2V2. So put all those numbers in and you'll get this volume here. So what that means is you need to grab this volume of this concentration and make it up to this volume with water. And there you go, you'll have a litre of 0.05 concentration. Okay, so 4 centimetres cubed of 12 molar solution needs to be added to make up 1 mil. So maybe adding 996 centimetres cubed to make up 1,000 centimetres cubed to make a litre. And then you'll have a whole litre, and the concentration will be 0.05 moles decimeters -3 moles per litre. Okay, so that's how it works. That's how you do dilutions. This other one here is actually in the syllabus. So I've done actually a lot of bile at uni, and this is just a bile thing, I think. So I had a careful look at when you would use it, and I've always used it in biology. And it says proteins, which is biology. So when you need a really large concentration factor, and for bacteria as well. When bacteria, you just get a plate and you put a sample there, and you put strokes there, and then strikes there, and strikes there, and strikes there, and that's a serial dilution. By just like pulling that across, it's like a 1 in whatever, and then that's another factor, another factor. It's a similar thing. You grab an initial solution, take out, in this case, we're taking out 100 microliters, mixing it. So you get the pipette and just shake it up and down, expel and insert quite a few times, and that's mixed. And then you grab 100 mils and do the same thing, 100 thing. So it's a factor of 10. So you can see it's an exponential dilution. And you only do that for things that are enormous, like bacterial concentrations or protein concentrations, and you need huge ranges. And that's called a serial dilution. So quite useful in bile. I don't think this is chem, but it's in your syllabus. So there you go. Now you know.